Good day, everyone. And once again, we're back together. All right, so we're looking at chemical equilibrium right now. So if you have not subscribed, please just make sure you're part of the family. All right, so taking this from the Eastern Cape 2023 May June. Right, so let's have a look at the question. They say the following reaction reaches equilibrium at a temperature of 200 degrees Celsius. And of course, we've got, I think it's a hypothetical reaction. Okay, all right, so we've got that reaction there. Now they say state Le Chatelier's principle. Of course, I think by now you should be able to not only state it but sing it. All right, of course, in a closed system, if one of the factors that affect equilibrium changes, then the equilibrium will oppose the change and a new equilibrium will be established. Okay, right. Of course, there are many ways to skin this cat, so you can state it in a way that seems comfortable to you. All right, so they say to us, two conditions must be met for a chemical reaction to establish equilibrium. One of the conditions is represented by the double arrow, okay, which means the reaction must be reversible. All right, state the other condition. Okay, so the other condition is what we stated in Le Chatelier's principle, that it must be a closed system. Okay, right, please remember that. So it definitely must be in a closed system. Okay, there we go. Right, now they say the reaction is initiated by heating 83.4 grams of PCl5, okay, in a sealed 2 cubic decimeter container. At equilibrium, it's found that the initial concentration of PCl5 has changed by X moles. Now, note has changed by, not changed to, right? So there's a difference there. They say show that the equilibrium constant rather is as expressed there. Right, so let's do this. Of course, we're going to draw our table, okay, and so that we can see what is what. And of course, I know that you guys usually like using that ratios first. Okay, you may do so. I won't in my case, but we will arrive to the same conclusion, right? So what do we have? We've got PCl5, PCl3, and Cl2, and all of them with a ratio of 1, right? So PCl5, PCl2, and Cl2. No, that was supposed to be PCl3, right? Okay, let's fix that there. So that's PCl3. Okay, so in this case, we've got an initial moles. Okay, we've got our change in moles, and we've got our equilibrium moles over there. That's in moles, and of course our equilibrium concentration, which is in moles per cubic decimeters. Right, now if you look at this, we started with an amount of PCl5. It was given to us in grams, okay, and of course we're going to obviously have to check on our periodic table there. I'll see if I can find one as quickly as we possibly can. Right, so we started with an amount in grams, and we need that to be in moles, right? Okay, let's go and check on our periodic table. So we've got 83.4 grams of PCl5. Now on our periodic table, there it is at the bottom there. We've got phosphorus, which is 31. Okay, and we've got chlorine, which is 35.5, right? Okay, so we're going to look for the number of moles. So we're going to say number of moles, that's mass divided by the molar mass. Okay, so we've got 83.4 grams. So that's 83.4 grams. divided by, now you've got PCl5, so you've got 31, which is for phosphorus, plus 5 times chlorine, which is 35.5. Okay, right, so let's quickly have that calculation. So that's, all right, so that's 83.5 divided by, okay, we've got 31 plus 5 times 35.5. Okay, all right, 35.5, and I get 0.4 moles from that, right? So my initial moles for PCl5 is 0.4, but now what you must keep in mind is that both PCl3 and Cl2 are both, in this case, products, and they did not say anything about them initially, so I'm going to assume that we started with 0. And remember now, they say to us that at equilibrium is found that the initial concentration of PCl5 has changed by X moles, right? So, which means that we've changed by a certain number of moles, in this case, when it comes to the initial concentration. In fact, I think it would have served us even better to draw this table in terms of concentrations, but I'm going to keep to moles because we've already done so in terms of I've already started with moles, right? So in this case, what I'm going to simply do, we know that the change has changed by X, but remember X moles per cubic decimeters, right? So how do I convert from X moles per cubic decimeters to moles? So in this case, if a number of moles, or rather concentration, is number of moles over volume, right? So my concentration is X, right? I want number of moles, and my volume, remember we're given a volume of 2 there, so that's going to be divided by 2. Okay, right, I'm going to take this right down so that we've got sufficient space. Okay, so which means that the number of moles that it would have changed by is 2x. Okay, so which means if I now go and substitute there, it means that this changed by 2x moles. All right, you just need to be careful between the moles and the moles per cubic decimeters, right? And of course, now, because we are using, in this case, it's a 1-to-1 ratio. For every 1 PCl5, we will produce 1 PCl3. So that means that this ratio will also be 2x there, and this will also be 2x over there, right? And of course, at the end, right at the end, we've got, okay, so we'll have 0.4 minus 2x. Okay, this is for PCl5. I started with 0.4, I used 2x. I've got 0.4 minus 2x. I started with nothing and I produced 2x. I've got 2x at the end, and I started as well, nothing, 2x, and I've got 2x at the end, right? And of course, to get concentration in this case, you say number of moles divided by the volume is 2. So if I take 0.4 minus 2x divide by 2, okay, that will give me 0.1 minus x. 0.2 minus x. Okay, so that will be 0.2 minus x. And of course, the concentration here is 2x divided by 2 will give me x. And of course, that will also give me x. Right, so if I want to calculate the equilibrium constant, right, so Kc, molar concentration of my products, which is PCl 3 rather, and Cl2, both of them in gaseous phase, so PCl3 multiplied by Cl2 divided by the molar concentration of my reactants, which is PCl5. Okay, right. And of course, when we substitute PCl3, that was X, this is X, okay, and in this case divided by PCl5, which was 0.2 minus X, okay, you remember that. And of course, our equilibrium concentration will be X squared divided by 0.2 minus X, right? And of course, this is what they had asked us to prove over there. All right, now please remember, you could have drawn this table using concentrations, so which means that you would have had moles per cubic decimeters there, okay? And of course, you would have had moles per cubic decimeters over there. So you wouldn't need this part here. So the initial calculation, you'll find out what PCl5 is initially in terms of concentration, right? And of course, you should be able to get to the same conclusion. All right. We found that answer, right? Let's find the next question. They say to us, the concentration of PCl5 at equilibrium is found to be 0.001. Okay, this is in moles per cubic decimeters. Okay, they say show by calculation that the value of Kc is equal to 39.601. Okay, so this is the easier part because we're just simply going to plug and play, right? So remember that PCl5, okay, was the guy at the bottom. So the 0.2 minus X, okay? So they say to us the concentration of this guy is found to be that 0.001. So what we're going to simply do, okay, let's just make some more space again. Okay, so that's 6.3.2. So in 6.3.2, we're going to say, well, 0.2 minus X, right, is equal to 0.001 rather, 0.001. So in order for us to find the value of X, so X, if I take X to the other side, I bring this guy to this side, and that will be 0.2 minus 0.001. Okay, so that will give us 0.199. Okay, that will be obviously our concentration in moles per cubic decimeters. But remember, what are we looking for? We're looking for the value of Kc, right? But we already have an expression, which is X squared over 0.2 minus X. Actually, we've actually found even this value here. So our X value, that's 0.199, okay, squared divided by, in this case, our 0.2 minus X was given as 0.001, okay, which was the concentration of PCl5. Right, so I don't know why I removed that value, 0.199, and we square that value. Okay, and we divide that by 0.001. Okay, and it gives us exactly the value that they asked for, which was 39.601. That's a very high Kc value. It tells us that the yield is quite high, right? So in 6.3.3, they're asking us, is there a low or a high yield at 200 degrees? And they want us to give a reason for the answer. Okay, so it will definitely be a high yield. So the yield is high. Okay, and the reason for that is that our Kc value is greater than 1. Okay, so remember that for a Kc value greater than 1, you will get a high yield, right? Okay, they say in 6.4, what effect will the addition of a suitable catalyst have on the following? They say choose from a decrease, increase, or no effect. Right, the percentage decomposition of PCl5. Now remember that the moment that we add a catalyst, we're going to increase the rate of the reaction, right? So, of course, the decomposition of PCl5 is the reaction there. So, definitely it will increase, the rate will increase. So, that's increases over there. All right, and 6.4.2, they say the time taken to reach equilibrium. Okay, so remember, again, we are increasing the rate of the reaction, so which means that the time that it takes to reach equilibrium will become shorter. Okay, so just be careful of that. So that time decreases. Okay, so meaning that we reach equilibrium much faster. All right, so let's go on to the last part of this question. They say to us the graph below shows changes of concentration of reagent PCl5 and Cl2 against time. All right. So they say to us, what does the horizontal section of the graph between 0 to T1 represent? Of course, that represents when the graph is at equilibrium. So it represents dynamic equilibrium, or we can say equilibrium there. Okay. Right. So it represents equilibrium. I'm going to write that down as soon as my pen allows me to. Okay. Yeah, this guy is really giving me an issue. Okay, so we might as well just write it at the bottom there. So for 6.5.1, okay, it simply means that we're having equilibrium. Yeah, technology can embarrass you at times, hey? Okay, so let me remove this guy over there. Right, so 6.5.2, they say at time T2, the temperature of the reaction of the equilibrium mixture is changed, right? Now they say, was the container cooled or heated at T2? Right, now I want you to please note, what happened is that whatever change in temperature, right, caused the products to increase. Can you see that, né? Right, so our products definitely show an increase there. So it must mean that whatever happened to temperature must have favored the forward reaction. Now let's go back to our reaction. They told us that we've got an endothermic reaction. So the forward reaction is endothermic. So which means how will we favor the forward reaction in this case? It means that we must have increased temperature, right? Because an increase in temperature will always favor the endothermic reaction. So let's answer that question. They say, was the container cooled or heated? So definitely our container must have been heated. Okay, so we are saying it must have been heated in this case, right? And of course, they're going to want us to explain that using Le Chatelier's principle, right? So remember, we say we state the change. So an increase in temperature favors the endothermic reaction. Endothermic reaction. This is a statement of fact. Okay, reaction. All right. The forward reaction is endothermic. Reaction reaction is endothermic. Okay, and therefore the forward reaction is favored. And so as a result, we see thereby an increase in the concentration of Cl2. All right, so therefore definitely the reaction was heated. All right, so that is how this cookie crumbles, ladies and gents. All right, so you would have gotten yourself a good 20 marks from that question, and I hope that it did help. Right, please continue to practice. Exams are just around the corner, ladies and gents. We are less than 40 days from the final exam, so I hope that you guys are intensifying your preparation as well. And of course, maybe some of you, I will be able to see you in my upcoming camp. All right. Otherwise, I'll see you guys next time. Sharp, sharp.